Could black holes be the key to a quantum theory of gravity, a deeper theory of how reality, of how space and time works?
Famous physicist Brian Cox has just announced that our universe exists inside of a black hole.
Black holes are interesting because we have a place called the event horizon, where we think that we have full control of the physics. We understand what's happening, but there is a fundamental clash between our two basic theories of nature, both quantum theory and general relativity together. And the quest to unify those two great pillars of 20th and 21st century physics into what's often referred to as a quantum theory of gravity is in some sense a holy grail for theoretical physicists. So black holes are forcing us into a deeper understanding of what space and time are. And in that sense, I think it is fair to say that black holes are the keys to understanding the universe.
Black holes are among the most intriguing and enigmatic phenomena in the universe. They're incredibly powerful, yet nearly invisible to us. A black hole with a mass of between 2 to 4 million times that of the Sun has been studied extensively over the past few decades. Our understanding has evolved from knowing little about them to gaining increasingly detailed insights. Recently, Brian Cox announced that we have finally glimpsed what lies inside of a black hole. He believes that our universe lies inside an enormous black hole. This new information sheds light on aspects that might have been overlooked by scientists. Join us as we explore deeper into black holes and reveal what's hidden in these cosmic giants.
Well, there's an event horizon surrounding the black hole. In some sense, it defines the boundary between the external universe and the interior of the black hole. And if you go across the boundary into the interior of this sphere, then even if you can travel as fast as the speed of light, you can't escape the gravitational pull of the black hole. But another description of the event horizon, which confused people all the way through the history of black hole research actually, was the idea that the event horizon, when viewed from the outside, is a place in space where time stops. And that's a direct prediction of Einstein's theory of relativity from the external perspective. There is a central problem, though, which is still not solved, which is what lies at the center of a black hole.
Before diving into Brian Cox's findings, it's important to cover some background. Despite having a general understanding of black holes, there are still some misconceptions. Albert Einstein's theory of general relativity, published in 1916, predicted the existence of black holes, but the concept was theoretical at the time. It wasn't until the 1960s that evidence for black holes was discovered. During studies of the Cygnus constellation, astronomers observed a bright blue star emitting X-rays, which turned out to be orbiting a massive object. This object was identified as a black hole because the X-rays were being drawn into it. This finding was crucial as it confirmed the existence of black holes, proving that they were not just a theoretical idea. This discovery spurred researchers worldwide to investigate these mysterious objects further. The black hole known as Cygnus X1 is located in the constellation of Cygnus, about 6,000 light-years from Earth. It's about 14 times brighter than the Sun and extremely dense, giving it a strong gravitational pull. This pull is so intense that even light cannot escape, which is why it's called a black hole. A black hole is a region of space where gravity is so powerful that nothing, including light, can escape from it. Anything that ventures too close is pulled in and lost forever. Despite the dangers, studying black holes is crucial for understanding more about the universe. Were we done, or was this just the beginning? It turned out to be the latter. After discovering X1, scientists began searching for more black holes and estimated there might be over 100 million in the Milky Way alone. Although detecting them is incredibly challenging, it's believed that there are several million black holes in our galaxy, making them crucial to study. The main issue with black holes is their gravity. Their gravitational pull is so strong that anything that enters gets compressed into a singularity. Essentially, black holes act like cosmic vacuum cleaners, pulling everything in. Research into black holes reveals a frightening detail. If someone were to fall into one, they would be stretched into a single line. Now, this would happen slowly, so the person would die before the process is complete. Fortunately, despite the presence of black holes, the closest one to Earth is 500 light-years away, which is far enough to avoid immediate danger. In 2021, scientists captured the first clear image of a black hole, specifically the M87 black hole. They took several photographs over multiple nights and combined them to create a complete image. This process revealed that a black hole has 3 distinct layers, not just a single void of nothingness as commonly thought. To reach the core of a black hole, one must first pass through these layers. The first layer is the event horizon, which marks the point of no return. And once crossed, you cannot escape and will be drawn into the black hole. Beyond that is the photon sphere, where light orbits the black hole. Any light that enters a black hole is trapped and cannot escape due to its intense gravitational pull. The third layer of a black hole is the singularity, where everything that falls in is compressed to an extremely small point. At the singularity, the density becomes infinite, and the laws of physics break down, making it impossible to predict what happens next. What complicates this further is that every black hole is unique. While they generally follow the same 3-layer structure, their specific behaviors can vary significantly. Unlike other astronomical objects, black holes can't be studied in detail using telescopes, adding to the challenge of understanding them. Scientists can only study black holes indirectly by observing the radiation they emit and the surrounding gas and dust. Sending a probe, like Voyager, inside a black hole is impossible because anything that crosses the event horizon is pulled toward the singularity and compressed to an infinitely small point. Therefore, it's not feasible to use such probes since they would be destroyed almost immediately. As a result, scientists must study black holes in a 2-dimensional manner, despite their 3-dimensional nature. Compounding the challenge, each black hole is unique, and the laws of physics as we know them break down inside the event horizon. This means traditional scientific methods are not applicable for studying black holes. Researchers have been active in studying black holes, leading to many intriguing theories. One prominent theory is that black holes form from collapsed stars. When a star uses up its fuel, it can no longer generate enough energy to counteract gravity. This causes the star to collapse inward, becoming smaller and denser. If the star is sufficiently massive, this collapse can continue until it turns into a singularity. To explore black holes further, NASA scientists focused on the core of the galaxy M87. They observed a powerful whirlpool of superhot hydrogen gas spinning at an incredible speed of 1.2 million miles per hour. Despite the immense force of the spinning gas disk, it did not break apart. Scientists determined that a massive object, equivalent to 2 to 3 billion suns, must be at the center of the galaxy to prevent certain effects from occurring. This mass is believed to be a black hole. The idea of spinning black holes was first described in 1963 by New Zealand mathematician Roy Kerr, who used Einstein's equations to model a spinning black hole. Kerr's work revealed that a spinning black hole does not collapse into a point, as previously thought, but instead forms a ring of fire or a thin disk. This disk, known as the ergosphere, spins so quickly that centrifugal forces prevent it from collapsing further. The ergosphere is the region around the black hole where the laws of physics start to break down. An interesting aspect of Kerr's solution is the prediction of an Einstein-Rosen bridge, or wormhole, a theoretical passage through space-time that could connect 2 separate regions of the universe, or even parallel universes. The idea is that if someone were to fall into a black hole, they might not be crushed, but instead be transported through a tunnel and emerge from a white hole in a parallel universe. To understand this, we need to consider the concept of space-time. According to Einstein's theory, space and time are interconnected, forming a 4-dimensional fabric known as space-time. Objects with mass warp this fabric, creating a gravitational field that draws other objects towards them. Imagine a sheet of paper representing space-time. If you place 2 points on the paper and draw a line between them, this shows how objects move through space-time. If you fold the paper in half, creating a shortcut between the 2 points, you get the basic idea of a wormhole, a shortcut through space-time that connects 2 distant points instantly. Wormholes are more than just a sci-fi idea. They're predicted by general relativity. While no one has observed a wormhole directly, they're thought to be unstable and would collapse almost immediately if created.
An Einstein-Rosen bridge, a type of wormhole, suggests that black holes might not only act as cosmic vacuum cleaners, but could also serve as portals to other regions of space-time. Could we use a wormhole for space and time travel? The answer is likely no, at least for now. Even if we could stabilize a wormhole, using it to travel faster than light would be unlikely. Einstein's theory of special relativity sets the speed of light as a limit on how fast anything can move through space-time. Nonetheless, the concept of wormholes and black holes as pathways to different parts of the universe, or even different times, has intrigued physicists for decades. The potential for shortcuts through space-time, allowing travel across vast distances or into the past, could be revolutionary if it were ever achievable. One interesting concept in this field is the Kerr wormhole, named after mathematician Roy Kerr, who first described it using Einstein's equations of gravity. A Kerr wormhole is a theoretical tunnel through space-time that might connect two distant points, such as different universes, or different times within the same universe. It's often imagined as a ring-shaped portal, similar to the looking glass in Alice in Wonderland. Just as Alice was transported to a world with strange rules, a Kerr wormhole could potentially move a traveler to a different universe or time with different physical laws. At the destination, however, those laws might seem normal. The concept of wormholes for interstellar or time travel is fascinating, but it also sparks controversy and debate among physicists. Some argue that wormholes, especially Kerr wormholes, might be unstable or impractical due to intense radiation or subatomic forces around their entrances. Critics point out that Einstein's equations, which describe wormholes and black holes, only address gravity and not the quantum forces affecting radiation and subatomic particles. To fully grasp these phenomena, a new theory is needed that combines gravity with quantum theory. This unified theory, known as the theory of everything, aims to merge Einstein's theory of gravity with quantum mechanics. Michio Kaku, a well-known theoretical physicist, has been developing a theory of everything for decades. Among the various proposed theories, superstring theory is the most promising. It aims to unify gravity with the theory of radiation by suggesting that subatomic particles are tiny vibrating strings, and that the universe operates like a symphony of these strings. Just as different musical notes correspond to different vibrations of a violin string, different particles correspond to different vibrations of a superstring. An intriguing aspect of superstring theory is that as a string moves through time, it distorts the fabric of space around it, leading to phenomena like black holes, wormholes, and other solutions to Einstein's equations. Superstring theory not only integrates Einstein's theory of gravity with quantum theory, but also addresses many of the mysterious phenomena observed in the universe. However, the theory's complexity becomes evident when considering its requirement for 10 dimensions of spacetime, as opposed to the 3 dimensions of space and 1 dimension of time we experience daily. Although it's challenging to visualize these additional dimensions, physicists have created conceptual models that help us understand them. Imagine a 2-dimensional pond where fish can only perceive length and width. For these fish, height doesn't exist, and they can't envision living in a 3-dimensional space. However, when rain falls and creates ripples, the fish see the impact of the 3rd dimension even though they can't directly experience it. Similarly, physicists believe that while we can't directly see extra dimensions of spacetime, we can observe their effects on our 3-dimensional world. Specifically, in superstring theory, vibrations of strings generate energy waves that travel through these extra dimensions. These waves can appear as particles with various properties, like mass and charge. Thus, superstring theory might account for all particles and forces in the universe, including gravity. There's a challenge with superstring theory. The extra dimensions of spacetime it proposes are so small that we can't observe them directly. Our most precise measurements only account for the 4 familiar dimensions of spacetime. So how can we confirm the existence of these extra dimensions? One possibility is that these extra dimensions are so tightly curled up that they're invisible to us. For instance, if a sheet of paper were tightly rolled into a cylinder, an ant walking on it might not notice the curvature. Similarly, the extra dimensions in superstring theory could be tightly curled into small loops or spirals that we can't see, yet still influence the behavior of these strings vibrating within them. One possibility is that the extra dimensions were more prominent at the start of the universe during the Big Bang. Some versions of superstring theory suggest that the universe initially existed in a 10-dimensional spacetime, with all dimensions visible. As the universe expanded and cooled, these extra dimensions began to collapse and curl up, leaving us with the 4 dimensions we observe today. If this is accurate,
we might detect traces of the extra dimensions around us. The mathematics of superstring theory is extremely complex and has introduced new areas of mathematics previously unexplored. However, solving the problem of a quantum black hole has been challenging, with no definitive solutions yet. Edward Witten of the Institute for Advanced Study at Princeton has referred to superstring theory as 21st century physics that fell accidentally into the 20th century. Last year, several groups of physicists made a major discovery. They showed that string theory might fully resolve the problem of a quantum black hole, though this applies only in 2 dimensions, not 10. Many physicists think it's only a matter of time before someone solves this problem, given that the equations are well-defined but challenging. Until then, it's still too early to consider intergalactic travel or time travel involving black holes. Despite these advances, one thing is clear. There are still many questions and numerous proposed solutions. Michio Kaku has discussed how to determine the correct answer among many theories. He pointed out that the issue of having infinite answers is not unique to string theory. Many significant theories, such as Newton's laws, can predict the motion of different objects, but you need to define what you're trying to explain to make accurate predictions. These specifications are known as initial conditions. In string theory, you also need to define what the theory is describing. However, unlike other theories, the initial conditions in string theory are the Big Bang itself. This means that you must specify the conditions of the Big Bang at the moment it was created, which are currently unknown. Understanding the initial conditions of the Big Bang in superstring theory involves delving into the earliest moments of the universe's existence. These conditions are fundamental because they set the stage for the universe's development and determine the nature of the particles and forces that we observe today. The Big Bang theory itself, as traditionally understood, describes a rapid expansion from a hot, dense state, but it doesn't specify the exact details of what came before or how the universe's dimensions were configured at that time. Superstring theory posits that the universe began with all 10 dimensions fully realized, but as it expanded, the extra dimensions compactified, or curled up into tiny loops or structures we discussed earlier. This compactification process could have occurred at scales so minuscule that they're beyond the reach of current experimental techniques. As a result, while the theory provides a framework for understanding how these dimensions might have behaved, confirming these ideas with empirical data remains a significant challenge. To make progress, physicists use various methods to infer the presence and effects of these extra dimensions. One approach involves studying high-energy particle collisions. When particles collide at extremely high energies, they can briefly probe higher dimensional spaces. These collisions might reveal signatures of extra dimensions through the production of particles or energy distributions that deviate from what is predicted by conventional 4-dimensional physics. The Large Hadron Collider, or the LHC, at CERN, for instance, is one of the most advanced tools used to explore these possibilities. Despite its impressive capabilities, it has yet to provide direct evidence of extra dimensions, but researchers remain hopeful that future experiments will yield more conclusive results. Another approach to understanding extra dimensions involves gravitational studies. According to some theories, the effects of extra dimensions could influence gravitational interactions. For example, gravity might leak into higher dimensions, weakening its apparent strength in our familiar 4-dimensional spacetime. Experiments designed to measure gravitational forces with high precision might detect anomalies that could be attributed to the presence of extra dimensions. Such experiments, though complex, could potentially provide indirect evidence of superstring theory's predictions. Astrophysical observations also offer potential clues. Certain cosmic phenomena, such as the behavior of black holes or the distribution of dark matter, may be influenced by the extra dimensions posited by superstring theory. For example, the study of primordial black holes, small black holes formed in the early universe, could offer insights into the nature of spacetime at very small scales. These black holes might exhibit behaviors that are consistent with the predictions of superstring theory, such as deviations in their Hawking radiation or their interactions with surrounding matter. Moreover, theoretical advancements continue to play a crucial role in the development of superstring theory. Physicists and mathematicians work on refining the mathematical models and developing new techniques to better understand the implications of the theory. String theorists explore various scenarios and solutions to the equations that describe the theory, aiming to make predictions that can be tested through experiments or observations. The interplay between theoretical work and experimental data is essential for validating or refuting the predictions of superstring theory. One of the key challenges in string theory research is its reliance on mathematical constructs that are not yet fully understood or developed. For instance, the concept of branes, multidimensional objects within the theory, adds complexity to the models. These branes can interact with one another and with the strings, leading to a rich and intricate set of phenomena that are still being explored. The mathematics of these interactions often involves advanced concepts such as topology and algebraic geometry, which are still being studied and refined. Additionally, superstring theory is closely related to other theoretical frameworks, such as quantum gravity and loop quantum gravity. These approaches seek to unify general relativity with quantum mechanics, and they offer different perspectives on the fundamental nature of space-time. Comparing and contrasting these theories helps physicists to test the robustness of superstring theory and to explore alternative explanations for the phenomena we observe. Despite its challenges, superstring theory remains a leading candidate for a unified theory of fundamental physics. Its ability to integrate various forces and particles into a single framework offers a compelling vision of how the universe operates at its most fundamental level. As research progresses, it's possible that new insights and breakthroughs will emerge, shedding light on the nature of the extra dimensions and the ultimate structure of the universe. Thanks for watching this video. Please share your thoughts in the comments below, and stay tuned for more content like this.